Okay everyone, in the last tutorial this week we are going to talk about arc length of curves and how to calculate them. So what we're going to do is just do some questions from chapter 5, and we're going to start off easily and then we'll move on to something a little bit more difficult. Okay, so as I go, I'll incorporate the questions into my solution, so you know you don't have to keep flicking through your set of questions. All right. So in the first question, we are asked to consider the curve described by the following function. Now, you'll see that we're only interested in the interval, the x values from 0 to 1, and we're asked to calculate the arc length of this curve. Now, there's a definite formula for the arc length. It relies. Anyone remember how you derive the formula? What the basic idea is? Yep. So I guess geometrically, triangles, right? It's Pythagoras' theorem, right? That's the basic way I remember the arc length formula anyway. Right. So I'm just going to let L denote the arc length. So by f dash here, I mean df dx. So the challenge then is to, in many cases with the computation, is to manage the square root sign away. Okay, sometimes it's easy, sometimes it's more difficult. So with this one, it's fairly easy. But let's actually go through and compute these parts and then see what our calculations give us. So I'm going to refer back to this. So let's calculate the derivative of our function. So it's going to be something like 3 on 2 x to the 1/2. And so we'll get the following. So this is going to be like 9 on 4x. Okay. Now, this is going to go in here. Now, when we integrate it, we're integrating, you know, the highest power is 1, right? I guess, you know, inside the square root sign. So is that going to be a problem for us to integrate? No. Okay, if it was a squared or something, it'd be a little bit more challenging, right? So it's not too bad. So our A and B are going to be the endpoints of our x interval. And this is 1 plus 9 on 4 times x dx. Now to integrate this, it's just the square root is going to go to a 3 on 2, and I just need to clean up by multiplication or division, I guess. So it's going to go to a 3 on 2. So I'll get something like that. So now when I plug in x equals 1 and x equals 0, I can clean this up a little bit, and I'll get something like this according to my calculations. Okay, and then if you want to sort of rearrange this, you can get the following. Okay? Right, so that's pretty easy, right? That's pretty easy on the difficulty scale. Now, this is a case where the function, or I guess the graph, is described using a function. Okay, y equals f of x. But there are other ways of describing graphs, right? You can describe them parametrically. You can describe curves using, there are other ways of describing curves, right? You can use a parametric representation. You can use, say, polar coordinates. So let's have a look at another fairly straightforward example. But here, we're going to, in the next example, we're going to use so-called parametric description. Okay, so this is 3 part C. So here is our basic description. So you can see the x-coordinate is a function of t, the y-coordinate's a function of t, and we're going from this point to this point in the plane, okay? So we're going from x equals 0, y equals 0 to x equals 8, y equals 8. So that's the curve. So our equations are in so-called parametric form. Now, the reason why it's important to distinguish between this example and the last example is that the arc length formula changes, right? Now, the first thing, so essentially what the arc length is going to be, it's going to be in terms of t and dt. We're going to be integrating something involving t. That should be, so that's a cube there, right? Okay. Now, let's firstly work out the interval, the t values that this curve actually goes between. So this is x value, this is a y value, this is an x value, this is a y value. Can anyone suggest how we might work out the t values for the endpoints? Yep. So what do you think the first point will the t value will represent? 0, right? Yeah. So t will be 0 there. And what about here? 2, right? Yep. So t equals 2. Yeah. So so just plug 0 in there, solve. T's got to be 0. Plug 8 in there and 4 in there. T's got to be 2. Okay, so the arc length in parametric form is the following. So x prime of t all squared plus y prime of t all squared dt. So you can see how it kind of, it's slightly different to the previous setup we had. Okay, so in this case, the alpha would be 0, the beta would be 2, and we just need to calculate the derivatives from this starred parametric setup. Okay, so I'm going to call this double star. So let's calculate these derivatives. X prime is going to be 3t squared. Y prime is going to be 2t. So let's square these, add them together, and see if we can manage this square root sign away. Okay, so let's square those. I'm going to get 9t to the power 4 plus 4t squared. Now you can see there's a common factor. We're going to have to take the square root of this. There's a common factor of t squared, and actually that's going to help us in the integral. So let's take this, put it back in here, and integrate from t equals 0 to t equals 2. Right, let's take out a factor of t squared in here, and that when we square root of it, it'll just give you t. So now again, we're at the position where we need to integrate this expression. We've got a 9t squared plus 4 inside the square root sign, but we can balance that with this of t, right? So when I integrate it, it's going to be something like 9t squared plus 4 all to the 3 on 2, and then I have to balance it up here, right? So I'm going to get 2/3, and the derivative of that's going to be 18, so I need to divide by 18. So all I need to do now is plug in t equals 2 and t equals 0 and take one away from the other.
How are you doing those integrals?
Okay, well, you can, if you really wanted to do it, you could do it by substitution. Okay, so you would let u, if you wanted to do this integral by substitution, you would let u equal 9t squared plus 4. Yep. You should, I mean, you should be able to run the, it's just the chain rule backwards, right? You should be able to do that. I mean, it'll take you a little bit. It'll take you a little bit to do it, but you should be able to do that by inspection, right? If you can't, that's okay. You've got backup. You can do it by substitution. But here, you only use substitution as a last resort, right? Only as a last resort. Okay, so if you sub in, according to my calcs, you get something like this, and then you can clean that up if you want to. So it's like the following. So that's a little bit different from the previous one, right? Now, you may think, okay, well, what does the graph of this look like? Anybody know? Anyone have an idea of how you might be able to find out what the graph of this sort of curve looks like? Well, what you can do is sort of, to put it in sort of a Cartesian form where you've just got x's and y's, you can sort of substitute out the t. So sort of make t the subject here, so you have t equals root y, and then sub that in there for t. So you get some sort of equation involving x and y, all right? Oh, okay, so onto the asteroid. So this is a good question. So let's consider the following equation. Equals. Now, this equation here, a is a positive constant. the graph, or I guess the curve associated with that equation, it describes a special curve known as an asteroid, not to be confused with an asteroid, okay? The asteroid comes from the Greek star-like shape. So what happens is it looks a little bit like this. Now, to get this shape, I've drawn it pretty badly here. What happens is, imagine there's a big circle going around here, and you've got a little circle that's rolling around the inside of the circle. Okay, it's a little bit hard to explain, but yeah, the dynamics of creating this asteroid is really quite beautiful. Now, we're asked to calculate the arc length. So in part A, we do that using a parameterized form. Okay, so let's solve it that way. So here are our parameterized type equations. Now the theta here is between 0 and 2 pi, okay? So you can think of that sort of doing one revolution. Okay, so to compute the arc length of the curve, what we're going to do is actually just basically compute one of these lengths and then multiply by 4. Okay. So what's the actual formula? Well, so we're going to use this setup here. So let's call that double star. So all we need to do is go here, calculate our derivatives, square them, add them together, and then see if we can simplify. Now, obviously, when we differentiate these things and square them, we're going to get some pretty involved functions. Okay, but hopefully, we can manage this square root sign away. So let's do that. All right, so to differentiate this, remember A is a constant here. This one's going to be, okay, well, you bring the 3 to the front, bring the derivative of cos to the front, and change the 3 to a 2. So it's going to be something like minus 3a sine theta cos squared theta. Does that look right? And y prime of theta, so bring the 3 to the front, bring the derivative of sine to the front, and decrease the power by 1. So that's going to be 3a cosine theta sine squared theta. So as you can see, it's pretty messy, right? We're going to have to square those and add them together. But don't be fooled, things are actually going to simplify quite nicely. Okay, so let's do our calculations. Now, we've got a common factor of 9a squared. And these don't quite match up, but what I'm going to do is turn this cosine theta all to the power 4 into cos squared times cos squared, and then change one of the cos squareds to 1 minus sine squared. Okay. So I'm just going to change this to cos squared, and then change one of the cos squareds to 1 minus sine squared theta. I mean, I'm sure you can do this. I'm sure you can do this other ways, right? Now, if you expand this, this term is going to cancel with one of these terms. So I'm only going to be left with sine squared theta, cos squared theta. Now, we're in a good position here because you've got to take the square root of this and then integrate it. So I've got all squareds, right? So let's sub back into double star, integrate from 0 to pi on 2, and then we'll multiply the whole thing by 4. So what we're doing is we're calculating this length here, and then we'll multiply it by 4 to get the final answer. So I can take the square roots. So we're pretty happy about that. And remember, a is a constant, so and greater than 0. And the other nice thing about keeping it in this interval here is that you don't need to worry about absolute values here. That's the other advantage in this approach, right? If you was you'd have to worry, oh, when is sine positive and when is it negative, and when's cosine positive, when is it negative. But here, we don't need to worry about that because these are both non-negative. So I can integrate this a number of ways. You can integrate this by parts. You can integrate it using a double angle formula. So you would change this to something like a half sine 2 theta. Or you can just integrate it by inspection using the chain rule backwards, right? The substitution. So that's the way I'm going to do it. So this will go to something like sine squared theta over 2. Okay, so you can do this at least 3 different ways. So if you sub in then, you're going to get, this is going to give you 1/2 in here, so 3a on 2. Now that's one part of the curve. The total arc length is 4L. You should get 6 times A. Okay, so that was the case where we used a parameterization to calculate the arc length, right? In the next part, in part B, what they ask you to do is actually use the function approach. So you want to rearrange this start equation and make y the subject, y equals f of x, and then use the slightly different arc length formula. So this is a little bit harder, a little bit more involved. So let's have a look at this. In particular, if you do it that way, you've got to look at what's known as an improper integral. So to set you up for that, they ask you to compute the following. Improper integral. Okay, the following improper integral. So I'm going to just denote this to be I. So the potential problem is that at x equals 0, okay, because our integrand, the function that we're integrating, isn't defined at x equals 0. So think back to first semester. An improper integral can just be written as a limit. Now, this improper integral exists if this limit exists, okay? So you do what's in the brackets first, do the integration first, and then the last thing you do is you take the limit. That's the last thing you do. So let's integrate here and see how we go. Now notice I'm approaching 0 from the right-hand side. That's because we're integrating from 0 to 1. If we were integrating, say, from -1 to 0 or something, it'd be 0 minus here. All right, so let's integrate. So increase the power by 1 and divide by the new power. So if I put in x equals 1, I'll get just 3 on 2 here. Put in x equals h, I'll get the following. Okay, so what's our limit going to be then? 3 on 2, because this goes to 0 as h goes to 0. So now the significance in this result is that we're going to use this in the second part of this question. Okay, so that's why they kind of just get you to do this little check to see that this improper integral actually is, exists. Okay, so in part II, what we do is we take this starred equation and make y the subject. So just basically we rearrange this, make y the subject, and then use the arc length formula in that form. So this is our function of x now. And the interval that we're interested in, the x interval, is from 0 to a. So to compute the arc length, we use the following. Now I'm going to use C and D here. In the previous, well, I guess the first example I used A and B, but the A could be confused with that, so I'm going to use C and D here. Okay, so let's take the derivative. So it's going to be a little bit messy. So what are we going to get? The 3 on 2 is going to come to the front. The derivative of what's in here is going to come to the front, and I'm going to decrease the 3 on 2 by 1. So what am I going to get? How does that look? That look all right? Now I can cancel some of these off. So 1 plus this all squared okay, it's going to be 1 plus all this squared. Now the square root, the 1/2 is going to cancel off. This is going to, the minus here is going to go to positive. This is going to go to minus 2/3. Okay. Now if you expand this, you'll see, well, this second term is going to become 1. So I'm going to get 1 minus 1, and I'm just left with one basic term here. So, to calculate the total curve, the length of the curve, what I'm going to do is, do this on this interval and then multiply by 4. So I'm just going to combine that into one step now. Okay, so this is going to go in here now. Okay. Now, I can clean up the indices with the square root sign. So I can, and remember A is a constant. So this is going to go to x to the minus 1/3. Now this integral over here is what we just did in part I. Okay. The only difference was in part I, we were integrating from 0 to 1, not 0 to a. But irrespective, we know that this is well defined. Okay, so we can go through and do the normal integration procedures. So let's just integrate here. Okay, so I'm sort of abusing some of the notation there, but then when you sub in, you'll get the following. So you can bring out the 3 on 2, and you get 6a to the 1/3. Now when you put in x equals 0, you get 0, and then it's just a to the 2/3. So what are we going to get here? 6a, right? We should get the same answer that we got for part A. So I guess that question is designed to show you that you can do these calculations sometimes 2 different ways, depending on what you prefer. Okay, so on to the first problem. The problems today basically are about arc length. Okay, so let's have a look at. So I'm starting at question 6 in chapter 5. So we're going to consider the cardioid described or parameterized by the following polar equation. Okay, so you would have seen this curve in first semester when you were graphing polar curves, right? Now, I'm just going to draw a rough sketch of the curve over here. Now, cardioid kind of gives you possibly an idea of what the graph might look like. Anybody remember what the cardioid looks like? Ah, well, it looks something like this. So it's a bit like a heart, okay? Over here it's 2, up here it's 1, minus 1. Okay? So a much better picture is this one that I've created earlier. Now, you can see in that picture, just using Maple, polar plot, you can see that actually the curve, it's not really heart-shaped, it's more like a peach or a plum, right? So anyway, this is how I just draw it. If I was drawing it in an exam, I'd probably be a little bit more careful. That we're asked to calculate the arc length of the curve. Okay, so we're working in polar coordinates here. So an arc length, it has a special formula for the arc length. And here it is. So now, probably the most challenging thing with these kind of integrals is managing the square root sign away. That's the difficulty, that's the challenge. Sometimes it's easy, sometimes it's not. In this particular example that we're going to do, it's not too bad. Okay, we're going to do one where it's really hard to manage the square roots on a way, but for this one, it's not too bad. So what we're going to do is calculate the derivative and put this in and then try to simplify. So let's calculate derivative dr d theta. So that's going to be something like minus sine theta. So r squared plus dr d theta all squared. So r equals 1 plus cos theta. So just take that, square it, and this is going to go to sine squared theta. Now, when we expand the bracket, we're going to get cos squared plus sine squared equals 1, right? So here we're going to get 2, 1 plus cos theta. Now, we're going to have to square root this and integrate it. Now, this doesn't look like the square of anything yet, but can anyone suggest how we can make what's in these brackets a square? Yeah, double angle formula, excellent. Okay, it's a little bit different because we're going to go from sort of theta to theta on 2, right? So it's a little bit different. Before we get to that though, what I'm going to do, see we've got some symmetry in the x-axis. So all I'm going to do is calculate the length of the top half of the curve and then multiply it by 2. Okay? Now if you integrated from 0 to 2 pi, if you did try to do 1 revolution, you're going to run into problems, I think. Okay? So here, I'm just going to restrict myself to the interval 0 to pi and then multiply it by 2. Okay, so let's just make a note of that. Total arc length is twice the length of the top half of the curve. So it's going to be 2 times the following integral. So it's the square root of all of this. Okay, I can take the root 2 out the front. And then I can change this to something involving sine squared theta on 2, right? Sorry, cos squared theta on 2, not sine squared theta on 2. Now, I can take the square root of 2 out again, and I don't need to worry about whether cosine is positive or negative here because it's always going to be positive. So take that square root out, I'll get 4 times this. And now I'm just integrating cosine theta on 2. So I'm going to have something like 2 sine theta on 2. And then I just need to plug these 2 in, and I'll get 8. Now, a couple of questions. Can anyone see another way of solving this integral by not going to this sort of double or half angle formula? Any other methods? Interesting idea. Even simpler than that. You might be able to use the T method. Okay, the method I'm thinking of is where you sort of look at, instead of 1 plus cos theta, 1 minus cos theta, and you multiply by square root 1 minus cos theta on square root 1 minus cos theta. Okay, so you would have something, you know, you would basically be multiplying by a factor of 1. So it would be 1 plus cos theta times root 1 minus cos theta over root 1 minus cos theta. So you're going to get a sine root sine squared up the top, you're going to get root 1 minus cos theta down the bottom, and you can just solve that by, either by inspection or substitution, okay? That's another way of doing it. You do have to be a little bit careful with this integral because you're integrating from 0 to pi. So if you want to be really correct about it, you have to have an improper integral there. Okay, so that's one other way of doing it. I think this is quicker, actually, the way that I've got it, but maybe I'm biased. How can you generate a cardioid? It's pretty simple. All you do is you take two circles, right, of equal radius, and you roll one around the outside of the other, and you have a point on the outside circle, and that sort of traces around this cardioid. Okay, it's a bit hard to visualize, but I plan to put an animated GIF in a bit later. So, yeah. Any questions for that one? All right. So that's pretty standard. Okay. Now the next question is a little bit more difficult. It's question 7. You've got a particle that is following the path, and the path is described by these parametric equations. So I think in the actual wording, it's a rocket that's launched or something like this. Okay. So the question is, find the point in time where the particle touches the ground again. So it gets fired from an elevated position in this case, and it flies through the air, and what's the time where it comes back to Earth? So can anyone suggest how we might sort of solve that problem? So, say again?
As in the first part, as in where it lands?
Yeah, well, the time taken for it to come back down to Earth.
So you make the y displacement 0.
Right, right. So it's basically just solving a quadratic. Okay, so I can cancel off. And then I can just factorize. Okay. Now I get two potential times here. In seconds, I think this is in seconds, right? So t1 could equal 9 seconds, or t1 could equal minus 1 second, right? Well, we know that our time's non-negative, so we'll just take t1 equals 9. Okay, pretty simple. Okay, so it gets progressively more challenging, these kind of problems. The next question is to calculate the speed of the particle at 9 seconds. Okay, so basically when just before it hits the ground, what's the speed? Speed of the particle, v, is just given by the following. Now, from a physics point of view, the speed here is just the magnitude of the velocity, okay? So you can think of this as being like a displacement vector if you write it as a sort of ordered pair. And then you can think of calculating the velocity, the vector, and then the magnitude of that velocity vector is just the speed, right? So let's calculate our derivatives. So this is going to be 40. And this is going to be minus 10t plus 40, all squared. So now I'm going to expand that bracket and see if I can simplify. Now I've got a common factor in here of 100, so I can take that out and square root it. So I should get something like this. So at t equals 9, so let's just plug in 9 over here. So in here I'm going to get something like 41. So 10 root 41 metres per second. Yeah, not too difficult, right? All you really need to know is the formula for the speed. Any questions? It's pretty straightforward, right? So let's get on to the next slightly more challenging part. Part C, we're asked to calculate the average height of the particle above the ground. So the average, so this is the way I'm going to basically denote the average, because y is all about the height. So anyone remember how you calculate the average of some function y over an interval?
Find the area under the curve and then divide by the length.
The length of the interval, right? Yeah, that's it, exactly right. So in this case, we know the journey is, well, okay, here it's going to, let me write out the general. Oops, sorry. So we're integrating from A to B here. We know that the journey lasts from 0 to 9. So all we've got to do is integrate this. Okay, so if I sub in t equals 9, t equals 0 is going to give me 0 in here. So if I plug in t equals 9, after some calculations, I'll get, I'm not going to put all the calculations in, but I should get 90 metres. All right, on to the most challenging part of this problem. It's been pretty reasonable so far, but the next part's fairly involved. Has anyone done part D? Yeah, it's hard, isn't it? Part D is hard. Anyone else done part D? I'd be pretty impressed. All right, let's have a look at part D. Part D is certainly the most challenging part of this question. What we're asked to do is calculate the distance travelled by the particle or the missile or whatever it is. For that, we need to calculate the arc length. Okay, so basically it is just the following. Now, because we've got a parameterization here, we use the parameterization for arc length, well, the parameterized type formula. Now, we've already calculated what's inside the radical sign from when we did the speed, right? We've already got that from back here. So I can actually just write that straight down. So it's going to be 10 t squared minus 8t plus 32 dt. Now, we don't have a perfect square in here. And the nasty thing is it's a quadratic. So I'm a little confused now. How did you guys do it?
Tried to complete the square.
Yeah.
But then
Is that how you did it as well, completing the square? Yeah, that's a good move. Okay, so I am going to complete the square. So to complete the square, what I'm going to do, you can do it a number of ways, but I'm just going to break this up. And so you'd break that 32 up into 16 plus 16 or something like that. You know, just take half this half this coefficient, square it, add it, take it away, all right, if you want to do it the other way. Now, how do we solve this? Well, I'm going to cheat a little bit here. I'm going to use a formula, but I'll tell you how to get it, okay? Basically, this is just u squared plus 4 squared du. Okay, so with u equals t minus 4. And it's the following. Oh. Okay, so where did this come from? Any ideas? Well, yeah, it's certainly substitution. You can do it a few different ways. The way I did it was let u equal something like 2 tan theta, and then the integral gets down to something involving sec cubed. Anybody remember how to integrate sec cubed? Yeah. Yeah. Well, okay. So you let u equal 2 tan theta. The whole thing breaks down to a sec cubed, right? You split the sec cubed up into sec squared times sec, right? And then you integrate by parts, and then you just rearrange. You know, when you integrate by parts and you get two sort of similar things and rearrange, that's where these halves come into it. Okay. Yeah. Good. Okay. So if we use this with u equals t minus 4, we obtain the following, okay? So you get the following. So L so this would be pretty impossible, I reckon, if you got it in an exam. You'd be pretty unhappy, I reckon. Because you wouldn't have time to do all the calculations. Okay, so it's looking a bit messy. And if you just sub in t equals 9 and t equals 0 carefully, when I subbed them in, I actually screwed up the calculation. So I was ready to email the director of first year saying, there is a mistake in the answers. No, I made a mistake. So if you carefully do that, you will get approximately 427.53 meters. Okay, now just coming back to this formula here, I'm just going to write down how you can verify that, okay? So just okay, so I mean, integrating sec cubed theta is like a bit of a challenge in itself. So, if you ran out of muscle for this problem, don't worry about it. Don't worry about it. Okay, so on to question 8. You can see we've got some sort of path parameterized by these equations here. Now, they're pretty messy, right? So that's kind of a turn off to begin with. We're asked to calculate the speed of the particle at any time t. We're asked to plot the graph of the speed function. And then we're asked to describe the path of the trajectory of the particle. So what path does the particle move along? What is the type of path? Okay, so let's have a look at this. So the first thing we want to calculate so it's just the following. Now, we have to calculate the derivatives of these. So it's a little bit nasty because you've got a cosine inside a cosine and a cosine inside a sine. So, you know, at a pinch, I can probably do this by inspection. But, you know, I mean, this is what I've come up with. It's a bit of a pain. In my rough notes, I've actually got the square roots on over 2 lines. So let's see if I put it in. Okay, so the derivative of what's in here is going to come to the front, right? So of what's in here, sorry. So I'm going to get something like pi squared on 2. The cosine's going to go to a negative sign. This cosine's going to go to a negative sign. So I'll just get sine pi t. This stays the same, and this changes to a sine, right? Again, you'd be pretty upset if you got this on an exam. Okay. So now let's just see what happens with this one. Well, the derivative of what's in this square brackets comes to the front. Yep. So it's actually we're going to get the same thing, right? So and this will go to a negative sign, right? But remember, I'm squaring all of these things. So squared, okay, I've got to put in the squared there, right? So this will go to a negative cosine. Can I fit it in? Come on. Yep. Oh, did I make it? Yes. All right. Now, this is a real mess, right? But if I look closely, when I expand these brackets, I'm going to get sine squared or cos squared plus sine squared. Okay, and I've got a common factor of all this squared. So I can use cos squared plus sine squared, and I'm going to get something like this, according to my calcs anyway. Yes? Hey. Now, when I take the square root, I need to be a little bit careful here, because this is for all t greater than 0. So sine of pi t is sometimes positive, sometimes negative. So to cover my bases, I need to just put in absolute value. All right, speed can't be negative. I guess that's important to remember. Okay. So assuming you can deal with this mess, not too bad. Not too bad. Let's have a look at the graph. All right, so when is this 0? It's 0 for t equals 0, 1, 2, 3, etc. So to draw the graph, okay, it'll have a maximum of pi squared on 2. And it's just going to look something like this. Okay, so this is 1, 2, 3, and so in between, that's where the curve or the speed is going to be a maximum. Sorry, max at 1/2, 3 on 2, etc. Okay. Now, believe it or not, this graph in B is going to help us sketch the graph of the trajectory, so the path that the actual particle follows. Okay, you can see that the velocity starts at 0, it goes up to pi squared on 2, then it goes back down to 0. So at t equals 1, t equals 2, t equals 3, the particle stops. Okay. Now for part C, they're asking you to calculate the actual curve of, or the path that the particle travels. Well, if you go back to our original equation, if we square both of these and add them together, we're going to get cos squared garbage plus sine squared garbage, right? We know that equals 1. So it's kind of like a circle, but not. Now don't worry, I'm not going to write out all that stuff. Right? Equals 1. It seems to be a circle with center 0, 0, radius 1. But no, that's not quite true. Okay, actually, again it comes down to here, right? You'll see what happens is the speed goes here and then it stops at t equals 1, and then it starts up again and it goes and then it stops at t equals 2. So what's actually going on here is the actual path travelled is the top half of the semicircle. Okay, and so basically what happens is that, this is just real basic. What happens is up here, the particle goes around, stops, and then comes back and stops, and then goes around and stops and comes back and stops. Okay, but let's actually prove it. I'm going to claim that the y here is always greater than or equal to 0 for all t. Okay, that means that it's basically always got to lie in the top half of the xy plane. Okay. Now, so to do that, what we're going to do is look at this and see if I can form some inequalities on this. Okay, we have the following. All right, so cos of pi t, we know that cos is between -1 and 1, right? So cos of pi t minus 1 is less than or equal to 0, but greater than or equal to -2. Now, to build this, all I need to do is multiply everything here by pi on 2. So multiply everything by pi on 2. Now, if this is between minus pi and 0, and we're taking the sine of this, what do you know about the sine of the sine function? It's got, well, yeah, less than or equal to 0, right? So non-positive. So that's good. And remember, y equals negative of this. So what that means is y, the particle's got to stay in the upper half plane. Okay, I think you've just got time to do the last question, or the last two questions. For part D, we're asked to calculate the length of the curve. Okay, so basically it's just, this is 1 here, so we know the length of this curve is going to be pi. Right? Now, in part E, what they're asking you to do is work out what happens, how far the particle travels after at t for 3 seconds, right? T equals 3. Now, to do that, what you do, right, is you go, okay, well, based on the speed, it's got to take 1 second. It stops, and then it goes back, and then it stops, and then it goes forward again. So it's going to be 3 seconds, okay? It's going to be 3 seconds. So basically what happens there is that this is the path travelled. That's up to t equals 1, then t equals 1 to 2, and then t equals 2 to 3, right? Kind of cute. So 3 times in 3 seconds. And so the distance travelled is 3 times this, which is 3 pi.